Hello everybody, we're going to take a quick look at atoms, molecules, ions, and nomenclature. And as we move to the second slide, of course there are many things in this chapter that you may want to read and be sure you understand, such as the history of the development of our knowledge of electrons and protons and neutrons and the structure of the atom. But the things we want to focus on here for just a moment are things like, what are the charges of these different particles? For example, you know that electrons are negative and protons are positive and neutrons are neutral. And so as we go through chemistry class, you're going to understand a little bit more about the interplay of these positive and negative charges and how they influence the chemical and physical properties of compounds and of elements. You may want to glance back and see things like how Ernest Rutherford, with his experiments using a beam of alpha particles, which basically they're just helium nuclei, were passed through a thin sheet of gold foil, and instead of just passing straight through and hitting a detector over here, which would have confirmed that the atom was kind of homogeneous in its structure because the particles just kind of went through. What was discovered was that some of the particles deflected slightly, and in fact some particles deflected back at very sharp angles. And this led Ernest Rutherford and his crew to decide that the atom had a very dense positive nucleus, and that's where most of the mass of the atom was located. So there are some of those kind of details you want to be sure you look at as you go through the chapter. But we are moving on. One of our objectives for this chapter is to be sure that you understand nuclear symbols like the one you see here on the screen. You understand, of course, that this is referring to lithium, and this is the atomic number, and sometimes you'll just see this referred to as the capital letter Z, and that capital letter Z tells us, of course, the number of protons that are in the nucleus. Now, sometimes you will see this symbol just with the 3 omitted, and the reason people do that is sometimes it's difficult to type the symbol the way you see it on the screen, and you already know that it's atomic number 3 simply because it's lithium. Up here we have the mass number. The mass number tells us the number of protons plus the number of neutrons. So if this number is different for the same element, for example, if we have lithium with a 7 up here, it would indicate a different isotope of lithium because there would have to be a different number of neutrons. In this isotope of lithium, there are 3 neutrons. In this isotope of lithium, there would be 4 neutrons. So that's how nuclear symbols work. Of course, we can also tell the charge if we are not dealing with an atom. Maybe we have an ion of lithium, and that charge can be indicated with a typical charge symbol that you're used to seeing. Now, of course, in this section of the book, we talk a little bit more about atoms, which are individual particles of an element, and sometimes we may just see that as Ag, and we assume that that is one atom of Ag. If we put a 2 in front of it, it is 2 atoms of Ag, 2 atoms of silver. Molecules are fastened together by bonds. And so sometimes we may see a molecule of hydrogen indicating there are 2 atoms of hydrogen and that there's a bond between those 2 atoms of hydrogen. Or maybe we see H2O indicating that this has an oxygen and 2 hydrogens, and that there are bonds between those atoms. And of course, the ion, such as the lithium that we were just looking at, indicating that there are more positive charges than negative charges. So this atom has lost an electron. So metals, of course, we know tend to lose electron and become positively charged, like calcium metal or aluminum metal ions. So those ions have lost electrons to become positively charged. Of course, nonmetals like chlorine tend to gain electrons and become negatively charged because they have gained additional negative charges. So that's how we determine if a species is an atom, a molecule, or an ion. You should be familiar with names of families on the periodic table and know something about their properties just based on their location. For example, here in this light yellow section we have the alkali metal family. Now, the alkali metal family we refer to as active metals, and you are aware, of course, that when you combine active metals, the alkali metal family, with water, if you're going to add water to it, plus H2O, you're going to always get hydrogen gas and the metal hydroxide. Methyl and the hydroxide ion. So you want to be sure you understand some of the properties of these families. The alkaline earth metals. And when we look at the chapter on periodic properties, we'll look at this in a little bit more detail, but you'll want to remember things like, as you move down this family, the properties change. And the alkali metals, those become more reactive, and the same is true here as you move down this family. They become more active. So, for example, if you put magnesium in water, it won't react quickly, spontaneously. But if you put calcium in water, it's much more reactive and it will react spontaneously. So you're going to want to be thinking about the properties of these compounds. But for now, be sure let's focus on the name. And we see here, there are the alkali metals in the first family, the alkaline earth metals, the transition metals, right here in this section of the periodic table. Noble gases, clear over to the right. And here's a family that's not named that you need to be sure you know the name of, the halogens. Halogens are particularly active nonmetals, very important to a lot of aspects of chemistry. So we'll be looking carefully at that group as we continue our study of chemistry. And in this chapter, we're learning to name 3 kinds of compounds. Binary compounds, which are composed of just 2 elements, so the word binary. We'll be looking at naming ionic compounds that have more, where the ions have more than one atom. So those won't be binary, they'll be polyatomic ions, and so we'll have at least 3 elements in the compound. Binary refers to just 2 elements in the compound. Polyatomic ionic compounds have more than 2 elements in the compound. And we will be learning to name acids that contain oxygen. So those are the 3 kinds of compounds we're going to learn to name in this chapter. So moving back here, let's see. If you look at any kind of compound and there are 2 elements in the compound, they will be a binary compound. Now, if there's a metal present, then you'll look at one of 2 things. Does the metal form more than one cation? Now let's glance back here at the periodic table and think about what metals form more than one cation. Now the metals that form more than one cation tend to come from this section of the periodic table, and the metals that only form one cation tend to be right around in here, although there are some other examples like zinc only forms +2. So you'll need to think about that as you're kind of learning the charges that metals form. Now, if the metal forms more than one kind of cation, you have to determine the charge of the cation and include the Roman numeral after that. So, for example, if we have iron, which forms more than one cation, we need to know something about its charge. So if we see iron in these 2 forms, FeCl2 or FeCl3, you will remember that these 2 very different compounds form differently because of the charge of the ions. Now, in order to balance these charges, of course we know that chloride has a charge of -1, and since there are 2 chlorides, the total charge of this cation must be +2. Here, the total charge of the cation, since there are 3 chlorides, the total charge of the cation must be 3+. So we have different names for these compounds, and we recognize that they're not the same compound, so they can't both be iron chloride, because then we would have no way of distinguishing which type of iron chloride we had in our bottle. So we use a Roman numeral, and the Roman numeral is the same as this charge. So our top example here would be iron 2 chloride, and our bottom example would be iron 3 chloride, where the Roman numeral comes from the charge of the cation. So we'll practice that in the assignment. Now, if the metal doesn't form more than one cation, we don't have to worry about the Roman numeral. So, for example, if we have calcium chloride only calcium cations only come in one charge, so we don't have to worry about including that in the name. And we can just write calcium chloride. So this is all about being able to distinguish the formula when we see the name or when we say the name. And this is the reason that we have to worry about this particular nomenclature. Now, let's erase this just for a moment and think about naming compounds where no, there we go, naming compounds where no metals are present. In other words, we just have non-metals. Just non-metals present. So, for example, if we see NO, we see that these are both capital letters, so we know they're two separate elements in the compound. We would call this nitrogen. We just put the name of the first element. Then we put the base name of the second element. We know that that's oxygen. And, we always, for the second element, use a prefix that tells us how many oxygen atoms are there. There's one oxygen atom. So we're going to say monoxide. Nitrogen monoxide. We always use the prefix for the second element. For the first element, if there's only one nitrogen, or one of whatever the first element is, we leave off the prefix. If we have, if we had N2O, then we would begin to use the prefixes. Di, meaning two, nitrogen monoxide. Or more commonly, we would have nitrogen trioxide or nitrogen dioxide. So be sure you learn those prefixes. Mon for one, di for two, tri for three. Now, what is the prefix if you have four elements, four atoms in the compound? Where do you look to find these prefixes in your book? Those are questions you're going to want to be sure you ask yourself. Page 64 has the prefixes used to indicate the number for the elements and names. And if you don't already know these, you're going to want to be sure you look. Of course, you're familiar with the game Tetris, where all the pieces are composed of four blocks. Tetra, meaning four. Penta. Hexa. Hepta. And octa. In reality, that's probably as high, definitely as high as you need to go for this, but for some organic chemistry things that we might look at, you will eventually want to know 9 and 10. Okay, moving on. What's next? Next, let's think for a moment about naming ionic compounds where we have polyatomic ions. Things like iron nitrate, we need to know, in order to know what the formula actually is, we need to know that this is iron 3 nitrate, and then this would be a 3 right here. So once again, we have to be sure we include the Roman numeral to tell us the charge of the cation, and that we use parentheses around the polyatomic ion if there are more than one of those ions present. Rules for naming acids. And there are a lot of these acids that we use on a regular basis, and then a few more acids like this that are kind of obscure and we're not likely to use in class, but you should understand the naming system so you can understand how to name all of them. And so here's the rule. We're going to look for the number of oxygen compared to the ion that ends with ATE. In other words, we know that there's an ion called carbonate. So we're looking here for ions that contain an element and oxygen, because we're naming oxygen containing acids, oxyacids. So we know that carbonate is CO3. Now the acid, of course, is simply putting on the right number of hydrogens to make carbonate, CO3. Of course, CO3 has a charge of 2 minus, so we're going to have 2 hydrogens here with our carbonate. So you might look at this compound and say, oh, looks like hydrogen carbonate. And you would be right, but we want to learn how to name it as an acid. So to name this as an acid, we find the anion, the polyatomic anion with the right number of oxygen to end in ATE. So this is carbonate. Now if we put hydrogen on that, we simply call the acid carbonic acid. We put the ending IC and we call it carbonic acid. Now if we take that carbonate and we have one less oxygen, so that's only 2 instead of 3, we are just taking away one of the oxygen, we have a different acid. And this different acid will have different compounds. In this case, it'll probably be a lot weaker acid. And we add the ending OUS. And so we have carbonous acid. Let's see, we're missing something here. Carbon OUS, carbonous acid. Now we still had 2 oxygens, so we could take one more oxygen away and have 2 less oxygen than the anion ending with ATE, and we would put the prefix hypo in the ending OUS. Now you know that hypo means lower than normal, less than normal, underneath, as in hypodermic needle, underneath the skin. So hypo means less oxygen, and we would call this hypocarbonous acid. Now moving the other direction, down to the very bottom of our table, we see one additional oxygen. So instead of CO3 -2, we have CO4 -2. Now here we see that we put the prefix per, which comes from hyper, as in excessive amount. So we have additional oxygen, and we call that percarbonic acid. So let's look at one more example of that, and this example is with phosphate. And a phosphate, of course, is PO4. Somehow didn't get all these changed the way they were supposed to be. There. That changed them all kind of almost right. So If there's one less oxygen, that would be PO3. So we'd have H3PO3 would be phosphorus acid. If we have two less oxygen, that would be H3PO2. That's two less oxygen. 1, 2. And we would have hypo at the beginning and OUS at the end, or hypophosphorus acid. If we have one additional oxygen, that would be H3PO5, it would be perphosphoric acid. So I think I have that corrected so it looks right. So those are the main topics we need to understand from Chapter 2, and we'll take a look at the assignment in a separate video.